So, in this session we are going to study the refraction that is due to a single spherical surface. So, consider a refracting surface, this is spherical surface, call it S, P, M, which separates two media. The media this side has a refractive index N1 and the media this side has a refractive index N2, which is suppose greater than N1. Now, this is the optic axis, and so let us assume a point object here and see how the ray from the object O after refraction meets here and forms a paraxial image. That is image formation due to this spherical surface we are going to consider. So, consider a OS a paraxial ray. This is the center of curvature of this surface. So, here you see this is the normal. If I join this point to the center of curvature, this is normal. So, this is called angle of incidence I. Now, the ray would have gone if there is no refraction, but since this is a denser medium, N2 is greater than N1, so the ray bends towards the normal, and so we get a paraxial image I. So, this I is the image of the point object O. We wish to know where is that image formed. So, we will use this distance. Let OP be denoted by X. I drop a small perpendicular here. So, this is so close that this point coincides with P. This is paraxial angle. If this angle is small, then the perpendicular here coincides with P. So, all distances are actually measured from here. Now, this distance is R, and let us assume that this distance from P to I is denoted by Y. These are the distances. Let us assume this angle to be theta 1 and this angle to be theta 2 and this angle to be phi, and this is your angle of refraction. With the normal, this refracted ray makes, so this is R. Now, we will apply Snell's law. So, applying Snell's law, N1 sin I becomes N2 sin R. This is the Snell's law at this surface. Now, since the angles are small, so we can write N1 sin I as only I into N2 R. So, sin I is I and sin R is R because these angles are small and this ray is paraxial ray. Now, you see this I, see this triangle SCO, this I is the external angle and this is equal to theta 1 plus phi. So, we can write N1 this I as theta 1 plus phi, that is equal to N2 R. Now, you see this triangle SIC, this phi is the external angle, this is the sum of this R and this theta 2. So, we can write phi, you see phi is equal to R plus theta 2 here. So, I want R1, so R1 I want R only. R will be equal to phi minus theta 2, phi minus theta 2. Now, let us bring this phi here. So, N1 theta 1 plus N2 theta 2 is equal to this N1 will go this side. So, N2 minus N1 by into phi. So, again this theta can be written as tan theta. So, N1 theta 1 is equal to SP by X plus N2 N2 times theta 2. Theta 2, this angle is so small that theta can be written as tan theta, Sp by y. Sp by y is equal to N2 minus N1. N2 minus N1, and this phi is Sp by r. Sp by r. So, this Sp cancels. N1 by x plus N2 by y is equal to N2 minus N1 by r. This is very important result. And now we are going to use the sign convention, our standard notion. Please take down this first. So, now let us use the sign convention using the coordinate sign convention, which we introduced in our previous session of reflection at spherical surface and mirrors. Distances are measured from pole, and this way the distances are negative. So, x will be denoted by here minus u, y will be denoted by plus v, and small r will be denoted by capital R, and this is plus r because this is that side. So, x means minus u. So, N1 by minus u plus y means v, N2 by v, that is equal to N2 minus N1 by r. So, simplifying is N2 by v minus N1 by u is N2 minus N1 by r. This is very important formula. This is the image formation due to this refraction due to a single curved surface. So, this is Gaussian formula for refraction at single surface. Please take down this is very important. So, now let us see the lateral or transverse magnification caused by refraction due to this spherical surface. This is the optic axis and SPM, the curved surface which separates two media of refractive index N1 and N2. Now, here we have an object AB. So, what happens? A ray here goes and bends, refracts, and so you see, let us see that this A dash B dash is its image formed. This height let us denote by H1 and this is height H2. This angle is theta 1 and this angle is theta 2. So, we will use Snell's law to relate theta 1 and theta 2. So, using Snell's law, N1 the refractive index of this medium into sine of theta is N2 sine theta 2. Now, these are paraxial rays, so I can write N1 sine theta as tan theta 1 and sine theta is here again tan theta 2. N1 I can write this, suppose I say this distance as x and this distance as y. So, I will get tan theta as h1 by x and n2 that is h2 by y, this distance y, this is. So, we get h2, this is h2 by h1, h2 by h1 is n1 by n2 y by x. Now, let us use our definition of lateral or transverse magnification. So, we define this lateral and transverse magnification as image height A dash B dash by AB. So, in terms of sign convention, if I have to put, This distance here you see, this is h2 and this is h1. So h2 by h1 is again minus n1 by n2 y by x. So again minus n1 by n2. Now y is v and x is minus u. So we have n1 v by n2 u. This is the expression of the transverse or lateral magnification caused by the refraction due to a single spherical surface. Please take down. So now let us see longitudinal or axial magnification for this case. So we have an object here whose length is along the axis, and I denote this as du. This is at a distance u, and suppose you got an image here that has a length dv which is at a distance v. So this longitudinal magnification is defined by image length dv by du. So in order to find this, we will use Gaussian formula. N2 by v minus n1 by u is n2 minus n1 by r. Taking the differential of both sides, taking the differential of both sides, minus n2 by v square dv minus n1 by u square du. If I differentiate 1 by u minus, so this will become plus, is equal to this side 0. So we have dv upon du, so will be equal to n1 by n2 v square by u square. So we see the longitudinal magnification or axial magnification, which we define as dv modulus of dv by modulus of u is equal to n1 by n2 v square by u square. This is v square by u square. This is the expression for axial magnification for this case. So now let us take an example to see how Gaussian formula can be used for a single surface. So example, if let us assume we have a diamond, this is spherical diamond. So now let us take an example of refraction at a single surface. This is my spherical diamond, half of which is silvered. This is diamond with a refractive index mu is equal to 2.4 suppose, and this is silvered. That means half of this is silvered, so this is reflecting side. Now we have a point object somewhere, we have to place a point object so that its image coincides with itself. So before this problem, we can take up another problem, a similar problem, but where curved surface is not, plane surface is used. So let us first see another problem. Suppose this is a spherical mirror kept vertically, and you see we have put some water into it, and this water is up to height h. It has a radius of curvature r. Now suppose the question is, if we place an object where should an object be placed so that its image coincides with itself? So that means this is, suppose I assume a ray here. Now this ray here bends. If we look from inside the water, we will find that this ray is coming out from a point mu, suppose this is x, so this will be mu x distance from the surface of water. Now, suppose when the ray falls on the mirror, and suppose this is normal incidence, this can be only possible when this point I is itself its center of curvature. That means this distance from this place is r. So, if this point and this point is at a distance r, that means this is h plus mu x, implies x is equal to r minus h by mu. So, whenever in optics we will get a situation where the image should form on itself, so we should try to use this idea that the ray should be incident normally on the reflecting surface. So, when this ray bends in such a way that it seems to be coming from the center of curvature of this mirror, that means it will be incident normally, and so it will retrace its path, and so finally image is formed on object itself. This is our idea. So, very important point, key point. So, whenever we have a case where image should coincide with the object, then we will consider this point that when the reflection take place, it should be reflected normally. Now, this idea is there. So, you see this idea when we try to adopt here, what is the trouble? Now, our problem is, this is a diamond, spherical diamond, half of this is silvered. The question is, where should an object be placed so that its image coincides with itself? So, sometimes we think that if this ray after refraction passes through the center of curvature of this reflecting surface, suppose this, then it will retrace back and image is formed. So, we are using this idea directly here, but there is a trouble here. You see, this point, this normal is normal to this surface as well as this surface. So, any ray going like this cannot pass through the center, it will bend like this. So, this will be some finite angle. If it passes, that means it has infinite refractive index. So, you see this ray cannot pass, and this model will not work for this problem. So, we have to think in a different way for this problem. Let us do that. Now, you see, the previous formula is not going, the concept is not going to be used here, because any ray incident like this cannot pass through the center of the diamond, because here the angle of refraction will become equal to 0. So, what we do, if this ray manages to reach here, then you see this angle and this angle will be same. So, it will get bounce in this direction, this will be symmetric, and due to symmetricity of the situation, this ray will go back to point O. So, if this is symmetrically reflected from this point, then it can form image here, and object and image will coincide. So, for this has to happen, we will apply the refraction at this surface. So, using Gaussian formula for the refraction at first surface, N2 by V minus N1 by U is N2 minus N1 by R. Here N2 is 2.4 given, N1 is 1 given, U has to be determined, V is plus 2R, and R is also plus R. R is equal to plus R, lying this side. So, N2 is 2.4 by V is 2R, minus N1 is 1, U has to be calculated, N2 is 2.4 minus 1 by R is R. 2.4 minus 1 is 1.4 by R. So, we see it is 2.4 by 2R minus 1 by U is equal to 1.4 by R. Let us simplify it. So, 1 by U becomes 2.4 by 2R minus 1.4 by R. So, you see 2 here only I can cancel it. So, let us write only R here and put this 2 here 1.2, it will become 1.2. So, now you see 1.2, this is minus 0.2 by R. So, implies U is equal to R by 0.2, that is 5R. That also minus. Minus indicates that it should be here. So, it should be 5R from this location. So, from this point the answer is, if you place an object at a 5R from this end, then its object and image is coinciding. So, now let us take another example. This is a quarter cylinder. Cylinder of glass with refractive index 1.5 and its radius is 5 centimeter. This glass is illuminated normally, this vertical face is illuminated normally by a parallel beam of light. What happens? This beam of light, after refraction from this quarter cylinder, falls on this horizontal plane. Let us determine what is the region of the horizontal plane which is illuminated by this light, where this patch of light will fall. So, what we do, just imagine a ray which here comes out grazing. That means here this C is the critical angle for, because it is denser medium and rarer medium. So, when it just grazes out, that means this angle is the critical angle for this. So, we can determine this C as sine inverse 1 by mu, that is sine inverse 2 by 3. This is 1.5, 3 by 2. Sine inverse 2 by 3 will be the angle. So, we know this angle C. So, we have this angle also C. So, once this is R, this is R. So, we can calculate what is this value of X. X can be calculated. That means, by using this sine trigonometry, this X can be calculated. Now, we know that this ray is going to fall here. And any ray, suppose I consider a ray like this. So, you see this angle will be more than this angle, critical angle. So, it will get reflected. It won't go this way because it will get reflected within this cylinder. So, all the ray, that means this ray is of no use. This ray is of no use. I will get only rays within this region. So, we get a feel that all the rays will be, the patch will be within this range, and this is our common mistake. Most of the students, when asked, they think that all the light will fall within this region. This is wrong. Let us see what is the problem. Now, let us see the paraxial rays, the rays which are very close to this. So, when the rays are very close to this, then these rays are normal incident, so they go as it is. But here this is a spherical surface and they form a paraxial image here. This is the paraxial image. To know, to locate this image I, we require to use Gaussian formula here. So, using Gaussian formula for the single surface. Gaussian, that is N2 by V minus N1 by U is N2 minus N1 by R. Now what is N2? Air. So 1. What is V? That has to be determined. What is N1? This 1.5 by U. U is the object is at infinity, the rays are parallel, so it is infinity. N2 is 1 minus N1 1.5 by R. You see R is lying this side, center of curvature, so minus R. So we have 1 by V, this 0.5, that is 2 by R. 1 minus 1.5 is 0.5, minus and minus minus cancel, so 1 by 2R implies V is equal to 2R. So now you see this 2R from this end, the image is formed. So all the rays, you see paraxial rays are formed here. So all the rays will fall within this region. All the ray will fall within this region. So we get a feel initially that the patch will be here, but actually the patch is beyond this point, this ray which is falling at the critical angle, and up to the point where due to this refracting surface the paraxial rays will meet and form the image. So now let us take an example, one more example. This is a spherical concave mirror. A concave mirror has the form of a hemisphere with a radius of r equal to 55 centimeter. A thin layer of an unknown transparent liquid, is here filled, is poured into this mirror, and it was found that the given optical system produces with the source in a certain position two real images. Two real images are formed for a certain position of the object, one of which coincides with the source. So we have two real images, one coinciding with the source and the other is at a distance of L equal to 30 centimeter from it. Find the refractive index N of the liquid. This is our problem. Now you see, suppose somewhere here as on this optical axis there is an object. It forms two real images, one coinciding with itself. So we may consider, so it gives us a clue that the object might be at here, and this is the center of the mirror without water, without the liquid. So this liquid is there. So this portion if I will remove, then this is the spherical mirror and this is the spherical mirror, and if an point object is placed, you see any ray going like this will retrace, and so its image will be formed, I1 will be formed on itself. So by getting this idea that we have two real images, one of which coincides with the source, this point gives us a clue that the object must be on the center of the hemisphere. So that because of this portion or even this portion, the rays, any ray falling here is going to rebound like this, and so its image will be formed here. Second image, now let us see that this portion of the mirror with the liquid is used. So any ray going like this refracts at this surface, and so then again it gets reflected and then again refracts, will form a image I2 which is said to be at a distance L from it. That means it is given that this distance is L. So if this is at L, then we have to calculate the refractive index of the liquid. This is our problem. So most of the geometrical optics problems, if we analyze the question only, then it will only give a clue that where is the object and why this is happening. So analyzing the problem is very important. So now let us see the image formed by this portion of the mirror, which is filled with the liquid. Because of this portion, the image coincides with the object. So now suppose this height is h, up to which liquid is filled. This h is very small. So suppose this is a ray, paraxial ray, then it bends and it seems to be coming from this point. Now suppose this is h, so here to here distance is r minus h. So this distance becomes r minus h. Here to here distance is r minus h. So this distance becomes r minus h into mu. This is the distance from this. We are going to neglect this h. We will neglect later on. So this I1 serves as an object for this mirror. Now this mirror reflects this light, and again in the absence of here refraction, the ray would have gone to this location I2, but actually the ray further bends and goes to this I. So this is my final image I. So it is said that the second image, that is the final image formed by this portion, is at a distance L from the object. So there is two images. By this portion one image is formed here. Because of this portion an image is formed which is displaced from that by a distance L. So now let us assume that this distance is x, this is x. So we use this mirror formula to get this point I. So using mirror formula 1 by V plus 1 by U is 1 by F. 1 by V. Because of mirror, the image is formed at I2. That means if this is x, then this is mu x. So I will write V as mu x. What is U? Now because of only mirror, the image object is I1, that is from this place it is mu r minus h, but from this place again plus h. So it will be mu times r minus h plus h is equal to 1 by f. So let us neglect this h. This is small, that the water is up to very less height. So this h can be neglecting h we get. So 1 by mu x plus 1 by mu r is equal to 1 by f. 1 by mu x is equal to 1 by f minus 1 by mu r, that is equal to f times mu r into mu r minus f. So mu x becomes f mu r. This mu will be cancelled out by mu r minus f. So mu cancels, implies x is equal to f r by mu r minus f. So we got x. Now let us see that this here to here distance is given as r. So r will be equal to this L plus x plus h. R will be equal to L plus x plus h. So we will put this value of x here, and neglecting this h, you will get r is equal to L plus x. So in place of x we will put f r by mu r minus f. Now let us simplify this term. Please take down this. So we have r minus L, bring this L, is equal to f r by mu r minus f. So r minus L into mu r minus f is equal to f r. So mu r square minus fr minus L mu r plus LF is equal to fr. So we can bring this fr here. So you have mu r square minus L mu r plus LF is equal to 2 fr. We can bring this mu here, that is r square minus LR, and this is, we can take F common, 2r minus L. So here again mu r minus L is equal to F 2r minus L. So F we have used the focal length, that is itself r minus L is equal to F is equal to r by 2. So we get this r cancel. So we have mu 2r minus L by 2 into r minus L. So thus we got mu is equal to this. So this is our mu. So thus the interesting part of the problem was that this was a mirror in which there was water, and the object is placed where we don't know. We have to find out where is the object also and what is the mu. It is given that because of this system, when an object is placed on this line, then there are two images formed. One image coincides with the object and another image is at a distance L. So you see, suppose I take this object as here, then you see this ray will bounce back and its one image I1 is formed here, and because of this another image I2 is formed, and this was displaced by L. So this was the problem. So come to the next problem. A narrow parallel beam of light rays is incident on a transparent sphere with a radius capital R and a refractive index n in the direction of one of the diameters. At what distance f from the center of the sphere will the rays be focused? So you see here we have a spherical glass ball of radius capital R. This is the center, and suppose this is radius R. We have a narrow beam of light. This distance is small compared to this R. The width of this beam is small compared to this R. It is asked to calculate where will these rays be focused. So you see here I observe that these rays are focused in my diagram like this. This is one possibility. Another possibility is that the rays will be focused here only. The rays can't be focused before this C. So one possibility is that the ray is focused here and another it is focused here. So first possibility and second possibility. So two possibilities are there. It will depend on how much is the refractive index that the ray is focused within itself, or it will be focused at this place. Let us find out. Now this is my sphere and this is the diameter. Suppose we have a parallel ray here. So this is my first refracting surface. The ray, suppose, goes like this. Suppose my case first is that it goes outside this. So if it goes outside, that means it will further bend like this. So this is my, so in the absence of this refracting surface, the first image is formed I1, but actually there is one more refraction, so this is I. So this is my first surface. Applying Gaussian formula formula for the first surface. So we have N2 by V minus N1 by U is N2 minus N1 by R. So here we have N2 is this medium and this is 1. So N2 is here, already we have taken N and this is N, and here N1 is equal to 1, this side air and this side also air, this is N. We have U is equal to infinity, V we have to calculate, and R is equal to plus R. You see the center of curvature C lies right of the pole. This is the refracting surface. So all distances will be measured from this end. So we will put this N2 as N by V, V we have to determine, minus N1, N1 is 1 by U is infinity, that is N2, N2 means N minus N1 1 by R is R. So this quantity becomes 0. So N by V is equal to N minus 1 by R, implies V is equal to NR by N minus 1. This is equation number 1. Now you see this ray seems to be going from to I1, that means from this place, this suppose this I call it P1 and I call this as P2. So we got P1 I1 is equal to V is equal to NR by N minus 1. Now if this image has to be formed this side, that means my P1 I1 should be greater than R, 2R. So if the final image or if the final image is to be formed outside the sphere, then P1 I1 should be greater than this point 2R. So P1 I1 is NR by N minus 1 is greater than 2R. So this R cancels, N should be greater than N minus 2N minus 2. So minus 2 comes this side 2. So N should be less than 2. P1 I1 should be greater than 2R. So N should be less than 2. So if N is less than 2, so let us write the condition here. If N is less than 2, then I will be outside the sphere. If N is equal to 2, then I will be on P2, this point. If N is greater than 2, then I will be within sphere. So these cases are very important. So depending on N, we will have these conditions. Now you see, suppose I want that the image is formed when. So when image is formed within sphere, then what will happen? Then the case will be something like this. The ray will go and meet here only. This is the center. Now you see, if I join from here this normal, you see the ray can bend only up to this. If mu is infinite, the ray can bend here, but we can't have mu infinite. So for large mu, the image will be formed finally here. And what will be the image distance from this center? So this Ci will be Pi minus this distance r. So already pi we have already calculated that pi is equal to this quantity nr by n minus 1 minus r, that is nr minus nr plus r by n minus 1, that nr cancels, that is equal to r by n minus 1. So from distance of I from the center, in that case will be r by n minus 1, and r will, n should be greater than 2, then only image is formed, then only the parallel rays will be focused here. Now if it is beyond this, if this ray is going to form like this, then again in order to calculate this distance, I have to again consider the refraction at this surface. Let us do so. First write down up to here. So now let us take the second case. We have already calculated P1 I1 as equal to nr by n minus 1. Now suppose the final rays is going here, so the second refraction will take place. Now consider the refraction at the second surface, at the second surface, this surface at P2. P2 is the pole for that. We will use N2 by V minus N1 by U as N2 minus N1 by R, the Gaussian formula. Here N2 is the medium in which the final air is going, that is 1. N1 is this medium N itself. U. Now here there is a chance of calculation mistake, U. Now here U, the object I1 serves as an image for this. So U will be P2 I1 will be equal to P2 I1, but this I1 is measured to be nr from this place. So we have nr by n minus 1 minus 2r. So this distance has to be subtracted. So this will give nr minus, this is 2r, 2nr minus 2r upon n minus 1. So this is nr by n minus 1 minus this 2r, that is nr, here nr, 2nr minus, so here plus will be there. So this 2r minus nr by n minus 1, this is your u. It's a very important point. So here there is a source of mistake. 90% of the calculation mistake we used to do here only. We calculate I1 from here, but when we put this second refraction, we have to see that this I1 should be calculated from this place. This is a common source of mistake. So now put this value N2 is 1, V has to be determined, minus N1 is N by U. U is this quantity, so it will be minus N minus 1 by 2 minus NR is equal to N2 minus N1, 1 minus N by R. Now its radius of curvature is lying this side, so this R will be minus. So we have now 1 by V as N into N minus 1 by 2 minus NR minus 1 minus N by R. So we can calculate V in this way. So this V will be again from here, and so the final location, that where is the final image, from this will be R plus P2I. So final F will be equal to R plus P2I, that is R plus what V we have calculated from here. So this is very important problem here. where we have to see two successive refraction from different spherical surface, and how this image formed by this acts as a virtual object for this refraction, and the final image I of a distant object is formed, or this is the final focus of this parallel rays.